I want to thank the organizers for inviting me to the special program on large deviations in statistical physics. I'm sorry I had to cancel my trip due to unavoidable circumstances, but modern technology allows me to have a virtual presence. I'm talking about an area roughly known as hydrodynamic scaling. What we'll try to accomplish is to use tools from large deviation theory to study scaling limits of large systems with conserved quantities. The evolution of the system is described at the microscopic scale. The interaction is very local. The conserved quantities, however, are observed at a macroscopic scale. They change slowly, governed by dynamics that's specified at the microscopic scale. We have to determine how the system evolves. We illustrate this by two closely related models. In both models, we have a system of size capital N that consists of scalar variables xi, which are located at sites I over n, equally spaced either at the periodic unit interval or the circle with unit circumference. The variables evolve in time according to the stochastic differential equation. The first one just expresses the conservation law, telling you that xi changes only due to inputs and outputs from neighboring sites. And the transmission from one side to another is governed by the relation, the second equation that we have. It has two terms. The first is the deterministic part, which has the effect of equalizing the variables xi at nearby locations, and it's however modulated by noise, which we assume is Brownian motion, which is independent for different bonds connecting I and I plus 1. With that, the entire vector of variables x1 through xn is an n-dimensional system, which is a Markov process, and it's easy to write down its infinitesimal generator. The interesting point to note in this generator is the derivative involved are not the usual partial derivative with respect to xi, but only the difference between partial derivative with respect to xi minus partial derivative with respect to xi plus 1. This reflects the fact that we have a conservation law, and any function that depends only on the sum of the variables is annihilated by L. We can rewrite L in a slightly modified form, which tells you that we have an invariant density given by Phi N of x, which is expressed here. And I mentioned here that the usual assumptions we make on little phi, think of it as something that looks like x squared, but not quite x squared. So it's sort of, maybe you can assume it's convex, bounded above and below by two different constants times x squared. So, although it's not really needed. So L is seen to be a self-adjoint operator with respect to the weight Phi N, and it has a Dirichlet form, which resembles the usual Dirichlet form, except that the role of the gradient is played by these successive differences. And you can always assume by adding a constant that phi is normalized, so that Phi N is a probability distribution. The sum is conserved, as we saw, and although Phi N is an invariant measure, like reversible invariant measure, it's not ergodic for the Markov process because of the conservation law. And so if you fix the mean at some particular value, then the conditional distributions are invariant measures, and they are in fact ergodic. Now, Cramé's theory of large deviations tells you that if you tilt the measure by an exponential weight to get a measure of mu lambda, m lambda being the normalizing constant, then the conditional distribution of xi, conditioned on the average being equal to m, converges as capital N goes to infinity to one of these things. And you can check that the mean is computed explicitly as the logarithmic derivative of the normalizing constant, and this expresses the relationship between m and lambda. And as capital N goes to infinity, the conditional distribution will converge to the product measure corresponding to the lambda. And one of the things we'll need later is the expected value of phi prime of x with respect to the tilted measure is just the amount of tilt. It's just proved just by integrating by parts. The duality relation of Cramer's large deviation theory is that if you look at the log of m lambda and look at the conjugate convex function, that's kind of an entropy, which is a function of m, and lambda is just derivative of h with respect to m. Now we'll be dealing with macroscopic states. The macroscopic state is just a function, rho of theta, from the unit interval or the unit circle to the real line. And corresponding to a given rho, we can construct a microscopic ensemble which is random. We just make the site, the variable at site I over n, be the distributed according to the tilt lambda of rho y over n, and you make it independent at different sites. This is a sort of a distribution on n-dimensional space, and you can explicitly write its density relative to the invariant density Phi N. And this is the explicit form. And this one can check just by law of large numbers that if you compute the profile, the macroscopic profile, which is computed in this manner, is just you think of a function that varies only at macroscopic scale, which is a function j of I over m. You weight it with xi and take the average. It's a weak limit of these functions with very oscillatory functions, and the weak limit defines, in fact, the macroscopic state. So a rho theta does not specify exactly what the individual xi's are. It roughly tells you some information about the xi's. The microstates, which are the diffusion process corresponding to the generator, they evolve according to n square. In other words, we speed up the macroscopic process by a factor of n square. Then the density relative to the equilibrium evolves according to the Kolmogorov forward equation, and at time t we'll have some distribution. And we want to show that although it's random with probability nearly 1, there is a macroscopic deterministic profile rho t theta, which is the limit of these objects defined weakly. So what we need to check is there is some rho t theta that satisfies this. And rho t theta then would be the macroscopic state of the distribution that evolves in time. So the goal is to describe how rho t evolves. Hopefully it evolves according to a PDE. And we can describe the PDE in terms of the function phi x that defines the problem. You have to make a computation. How it changes, you compute d of this. The first line just tells you you're computing it and multiplying by n squared because you have speeded up the time by a factor of n squared. And you apply the formula for xit, and that's the second line. The third line, I omitted one term, I omitted the noise term, and you can see a simple calculation tells you that the noise vanishes as capital N goes to infinity. It's just a Brownian motion, independent Brownian motions, and you can calculate the variance due to various factors. The fact that time is speeded up by n squared tells you the variance goes up like n squared. There are n bonds, so there are so total contribution to the variance is n cubed, but they're dividing by various things, and it gets divided by n to the 4 at some point, and so the variance goes to 0. So noise becomes irrelevant at some point. So you assemble the terms, and basically what matters is this object. And notice that this object, you can do summation by part twice, and the second derivative gives you an n squared, 1 over n squared, and then you can see that it's roughly the second derivative of j comes in, and then you have to know that if the exercise on the average is rho, that's what's meant by the macroscopic state is rho locally near theta, then the expected value of phi prime being lambda, then lambda as a function of theta is given by h prime rho theta. And so by some approximation, one could expect to prove such a relation. And that leads to the possible choice of a PDE for rho, which is of this form. And d is just the second derivative of h with respect to n rho, and is strictly positive because h is convex. The proof uses entropy and the Dirichlet form. The entropy is relative to the equilibrium distribution Phi N of x, and if you have a microscopic state distributed according to a density Gn relative to the invariant distribution, then its entropy is the integral of G log G with respect to Phi N. Now the entropy decreases according to the flow. That's easy to see. And in fact, one can write down a formula for the rate at which entropy decreases. If you compute it, you find it's basically the Dirichlet form which controls the rate of decrease of the entropy. But it's however the Dirichlet form for the square root of the density rather than the density itself. Notice that the Dirichlet form is geared more towards an L2 theory, whereas the density is an L1 object, and so we have to somehow compute the Dirichlet form of the square root to be the derivative of the entropy. Anyway, it's a simple calculation, noticing the fact that Gn satisfies in T the Kolmogorov equation, which being symmetric, backward and forward equations are about the same. Anyway, it's a computation that one can easily make, and then one obtains this formula for the rate of change of the entropy. That formula has an interesting piece of information. Entropy is always non-negative. And so from its initial value, it's always decreasing. And this is the amount by which it decreases. So if you integrate the amount by which it decreases all the way from 0 to infinity, it cannot increase where h and 0 where you started. In other words, if you look at integral 0 to t, the Dirichlet form integrated from 0 to t cannot exceed the initial entropy divided by n squared, because you speeded up the dynamics by n squared, so the Dirichlet form gets an extra factor of n squared. So if your initial entropy, which is usually proportional to the volume, so it's natural to assume that initially your entropy was bounded by constant times n, then the Dirichlet form, the integral from 0 to infinity, in fact, in particular from 0 to t, is dominated by a constant over n. This is a very useful information, and one can extract a lot of things from it. So if you look at average of a function f, which is not a conserved quantity, so one wants to know what its limit is as n goes to infinity. If you know that xi's have a profile asymptotically, which is a density profile that we described before, then if you take a function f of xi and take its average, does it have a profile? And what is the profile of it? And how is it related to the profile of xi? And we do it in several steps. First, you take an average of f of xi over a block of size 2k plus 1. So you're replacing it by this average. Notice they can shift the average to the j by just rewriting the sum. And j is very slowly varying. So over k sites, it's going to differ only by k over n. For fixed k, it goes to 0 as n goes to infinity, no matter what k is. So you can always replace the first term by the second term. Now if k is finite by large, then the Dirichlet form is nearly 0 for that block. Now if the Dirichlet form is nearly 0, that means the distribution is very nearly the invariant distribution. If it's an invariant distribution, and if the mean is nearly x bar, and if k is large, then its distribution is the tilted distribution according to Cramer. And therefore you can compute the average of f as just f bar of x bar ik, where f bar is defined as the integral of f with respect to the tilted lambda and the amount of tilt determined by m, basically. But that's not enough, because we got to replace now x bar ik with large K by x bar I n epsilon, or small macro scale. So in other words, we have to make a jump from large micro scale to small macro scale. So that means showing that there are no intermediary scales that are relevant. And to prove that, one uses again the Dirichlet form. And we'll get to that in a bit. And once you have that, then you conclude when the limit this goes to f bar over theta j theta d theta. This is true then for any f. And the reason why we can do that is if you look at the Dirichlet form, it tells you the Dirichlet form is the sum over all the bonds, and its total is C over N. So each bond contributes on the average only order 1 over N square. So if you want to link a bond to a bond which is a site to a site which is a distance n epsilon away, you can do it by a telescopic sum of n epsilon such bonds, and then by Schwarz's inequality, this will require a Dirichlet form which is n square epsilon square times the Dirichlet form for a bond. And since bonds have typically 1 over n square, when you work it out, you still have a Dirichlet form which is of order epsilon square. And so if epsilon is small, we can make this transition. And so one can succeed in replacing x bar ik by x bar in epsilon. It's a little technical, one has to actually get the estimates to prove it, but it's all in the Dirichlet form. And basically, it's not a difficult thing to show. Now, how do we actually structure the proof? So we start with a distribution which is distribution of the stochastic process, which are measure valued functions of t, and the measures are measures in S, and it's just the distribution with mass xi dot xi of t at I over n various points. So it's not really a real measure, it's a signed measure, but it shouldn't bother us. First thing we want to show is that this sequence Pn is tight, and you can take a weak limit P. What can you tell about P? Well, you look at the object psi and t, which is a basic weighted average of xi's. Think of it as a stochastic process. And you can compute dc and t, which you already did. It's sum dA and t plus dm and t. dm and t is the noise part, and that we saw goes to 0. So what you get is dA and t, which we saw was basically can be reduced to this object. That was the argument we had before. And m and t goes to 0 in mean square. So if you assume that initially you have a macroscopic state defined by rho naught, then almost surely with respect to P, in a weak sense, we have a solution of this equation in the integrated form. And you need to prove then uniqueness of weak solutions of this equation. Now, to prove uniqueness of such weak solutions, we need to have some control, some initial a priori estimates on P. Turns out, in this context, the estimates we need are of this form. You need to show that on the average, the entropy, the macroscopic entropy, the supremum of that over all T is uniformly bounded. And some kind of an energy function involving the derivative of rho with respect to theta should be uniformly bounded. So let's look at the first one. We'll tell you how to prove the first one, then the second one is somewhat similar. The whole idea is when you use large deviations, proving the first one is basically proving this inequality, because the entropy is convex function. You can dualize it and you just have a supremum over a bunch of things. So you want to show that the expected value of the supremum is bounded by C. It may be a lot easier to prove the supremum of the expectation is finite. That's easier, perhaps easier. So if you can take the sup out of the expectation and move it in front of the expectation, then the problem becomes much easier. But large deviations allows you to do it just by waving your hands. Let's see that. Jensen's inequality says that if expected value of e to the x is bounded by 1, then expected value of x is less than or equal to 0. So if mu n is a family of probability distributions that converge weakly to mu, think of it as distribution, two-dimensional distributions of random variable x and y. So you have bounds like e to the nx, d mu n is bounded by a constant, exponentially growing with the exponential constant. Similarly for y. So it's clear from this, in the limit you will get integral x d mu is less than or equal to c, and integral y d mu is also less than or equal to c. Actually, I claim that integral of max xy is less than or equal to c. So you can throw in the max for free. Because you can write the max xy simply as the limit of 1 over n log of e to the nx plus e to the ny. We have an estimate of e to the nx, we have an estimate of e to the ny, and so we have an estimate of e to the nx plus e to the ny, which is just twice e to the cn. So you get an extra factor of log 2 over n. Well, as n goes to infinity, log 2 over n goes to 0. So you get for max xy a bound which is exactly the same bound as you have for each one. So throwing the max in does not change your bound. So you can throw a finite number of max, an infinite number of max, a countable number of max, an uncountable number of max, as many max as you like. And the bound doesn't change. So we can move the sup out and then the estimate is trivial. We are interested in establishing large deviation properties for the hydrodynamic scaling that we considered earlier. We can think of our earlier presentation as proving law of large numbers, and there's naturally large deviations that go with it. But the essential step we need in proving the large deviation is the ability to consider the replacement lemma, which was replacing the average of phi prime by the integral of lambda. This had some error in doing this at a finite stage, and we want the error to a small probability, and that allowed us to do the replacement and the convergence in probability. But if you want to prove large deviations and you want to do this replacement, the error probability in the replacement has to be much smaller than any exponential, because otherwise it will interfere with the large deviation rate function. So what we need is to show that the probability that the error is bigger than epsilon is super exponentially small. For that, you look at the error, and the error is usually in integrated form. So there is a function v which tells you what the error is, and you integrate it from 0 to t, that's the error that's involved. And you want to make sure that the probability that this is bigger than epsilon is super exponentially small. The way of estimating such things by Chebyshev inequality is to compute these expectations and show that these expectations do not grow exponentially no matter what c is. And estimating such integrals involve Feynman-Kautz formula. Feynman-Kautz formula leads to bound in terms of a variation formula for these integrals. The variation formula is really Ritz variation formula, which involves a potential and a Dirichlet form. And if you look at it carefully, V is of order 1, and the term that there on the left is multiplied by n. On the other hand, Dirichlet form is multiplied by n squared. So it's clear in this variation formula, only Dirichlet forms which are of order c over n will play a role. But if the Dirichlet form is of order c over n, no matter what c is, then the approximations are valid with error probability that goes to 0. So it tells you that these expectations grow slower than any exponential growth, and therefore you have super exponential estimate for the error probabilities. And another place where we need this is when we make perturbations in proving large deviations. For establishing lower bound, we often perturb the dynamics so that we reach the new process as a limit. So that requires, for the perturbation, the entropy to be of order n, and we want to show that when the entropy is of order n, the replacement lemma still holds. So we need to estimate for any q, measure q, which is relative entropy with respect to p bounded by n. If p of a is super exponentially small, then we want to show q of a is small. And that requires an estimate of this type. So here's an estimate which shows you that if p of a is super exponentially small, then log pa is very big relative to entropy, and so q of a is small. This inequality just comes from the duality from e to the x and x log x, just like Holder inequalities come from the duality between x to the p and x to the q. A slight variation of this problem is when the Dirichlet form has an extra term. So we modify it by throwing in the function a of xy, which multiplies the square of the derivatives. This adds an extra bit of nonlinearity to the problem. Phi N of x is still the invariant measure, and the process is still reversible, and the infinitesimal generator can be written down, and it takes this form. The only difference now is if you apply the generator to the average of xi, earlier we ended up with the second difference of phi prime, and by summation by parts, we could transfer it to the second difference of j, which had an extra term, which gave 1 over n square, because j was slowly varying, and that 1 over n square cancelled with the n square. So we ended up again with an average now of j double prime and phi prime of xi. And then we were able to replace it with lambda. But now you can do summation by part only once, and when you do that, you end up with the term on the right, where w is a function given below. Notice that if a is 1, then w reduces to phi prime y minus phi prime x, and then you can do another summation by parts. But now, as of now, you are stuck with what you have. And the expression you have is of order n, because w is a bounded function, and that doesn't telescope, and so you are left with something that is really of order n. But you don't really need to estimate w, you only need to estimate the integral of w over an interval 0 to t. Maybe there's a lot of cancellation, and so the object of order n, when integrated over time, is of only order 1. Notice the dynamics is speeded up, so the integral from 0 to t is really like an average 1 over n square, integral 0 to n square t, and it's reasonable that a mean zero object, when integrated from 0 to n square, is really of order n and not order n square. So there is some hope here. So let's take a local function f of x and consider Ito's formula applied to the function 1 over n squared times the summation, and it reduces to something dt plus a martingale. Now the martingale part, you can compute its mean square, fairly straightforward. There are time is n square, so each individual martingale term has a mean square of order n square, and there are n such things, so the total mean square is of order n cubed. But you are dividing by 1 over n square, so the mean square gets divided by 1 over n to the 4, and so it still goes to 0. The first term is bounded by constant over n, because there are only n terms, each of which is of order 1, and you are dividing by n squared, so that goes to 0. So in the end, the first and the third terms are negligible, and that makes the middle term negligible too. But the middle term, if you look at it, it looks exactly like the integral of w, except it's not w, it's some other function. So that tells you there are a lot of functions looking like w, for which integral 0 to t summation without normalization is negligible. That means maybe you can find a constant c that depends on lambda, such that if you look at the integral of w and subtract from it the integral of some EAF for some f, then the difference may reduce to a gradient of phi prime. So this such a c, if you can find, will still allow us to replace w by c times phi prime. And if you can succeed this in doing it locally, even when lambda is not a constant, then you can reduce it to establishing the, then you will end up with the following partial differential equation. The only difference from the earlier one being that instead of just h double prime, now you have c as a function of h prime times h double prime. Now to understand this, suppose you have a stationary ergodic Markov process with generator L, and LF is minus V and LG is minus U. It's a reversible process. And you have Ito's formula, allows you to calculate the mean square of integral 0 to t as proportional to t with a constant which is twice the Dirichlet form of f. You can also compute the inner product between two such things. That's also computed to be twice the inner product in the Dirichlet space, and if you can also compute it as inner product in L2 of suitable functions. So you pick a lambda, and then you pick mu corresponding to mu lambda, and consider the product measured on the entire integers z, and call that measure mu, and look at the process with this invariant measure. So you take a local function f and consider the formal sum, which is the sum of x translates of f by tau I. Tau I is just a shift. For example, if f of x is x, tau 1 of, if f of x is x1, then tau 1 of x1 would be x2, and so on. So you compute this sum, The sum really doesn't exist because it's an infinite sum and there is nothing to make the terms go to zero, so it's brutally divergent sum. But on the other hand, the gradients, partial derivatives, and d by dx1 minus d by dx2, these things exist because each variable xi can occur only a finite many terms in the summation, and so these things are well defined. And if you have a function v, which is L of f, and you want to compute the central limit theorem variance, you can compute it and leads to the norm, which you can think of it as the norm in your space of a times cf squared. This is just an easy computation of the Dirichlet form of something that's translation invariant object is easy to compute. Now the space of such gradients psi of the forms d by dx1 minus d by dx2 of S form a space, and this space is characterized by certain properties. For example, you can compute d by dxi minus d by dxi plus 1 from d by dx1 minus d by dx2 by just shifting, because the original function S was translation invariant, so all the derivatives will be covariant. So the derivative with respect to xi plus 1 can be obtained by shifting the derivative with respect to x1. So dx1 minus dx2 generates all the others. And they have some consistency properties because the derivatives commute. And dA minus dA plus 1 applied to psi j is the same as dj minus dj plus 1 applied to psi I. And you can ask the question, what if I consider function psi in L2 which have all these required properties? Well, of course, if you look at the span of psi f and close it up and you call that Hilbert space H0, they will have all these properties. But there will be other functions that have these properties, and that defines a slightly larger Hilbert space H. So the question is, are there things in H that are not in H0? Well, everything in H0 has mean 0 because it's the difference d by dx1 minus d by dx2. They both have the same expectation. So if you have a psi which is satisfied the consistency relations, but mean is not 0, that's in H but not in H0. Well, there is an object, namely the constant 1. It's clear that it's a gradient, and it's clear it's not mean 0. And there is a theorem which says that H0 and 1 generate everything. So if you have something in H which is mean 0, it's actually in H0. That can be proved. And so now we have a representation for C which tells you C is in fact the infimum over F of this object. So in other words, the norm square of the projection of 1 into the orthogonal complement in this Hilbert space, orthogonal complement of H0 in this Hilbert space. This needs an explanation. There are 3 types of local functions with mean 0 and every mu lambda. There are W, there are function G, which is phi prime of x1 minus phi prime of x2, and there are things in the form LF. And you can try to define for all of these things the central limit theorem variance space-time computed as we did before. And we saw that if LF is minus V, this variance is just the norm square of psi f. So any psi not in H0 or H0 can span H. That can be either W or G. It's not easy to find a psi that represents G, but any psi that there is a psi, one can prove that the psi exists, and it's in fact orthogonal to H0. The orthogonality is easy to check because G telescopes, and when you compute the relevant inner product, because of the telescoping property of G, it's really order 1, and so you divide by 2k plus 1, it goes to 0. So the question really now, you want to take W and project it into the orthogonal complement of H0, and you want to compute what the norm square is. So you want W minus the multiple PG to be in H0. And then P times G would be the orthogonal projection. So that means W minus PG must be orthogonal to G. And that allows you to compute P to be the inner product between W and G divided by the norm square of G. And one can compute the inner product with W and G. It's a little bit complicated, but it's not that difficult to compute it because W is really L of something, but if L of something not really well defined, turns out to be, if you compute summation of xi, I bigger than or equal to 0, and call that function which really doesn't exist as f, then L of f turns out to be W. But in any case, although it's not very well defined, this inner product between W and G can be computed, and it's equal to 1. That means the norm of PG is equal to C, which reduces to P equals C, and that concludes our presentation. Thank you very much for your patience, and I'm sorry I couldn't be there in person, but thanks.